Hello to Dr. Narashikin and my fellow friend. Today, I'm from subgroup 8 with my fellow friend Afifah and Nur Nazira. We'll be presenting our poster with the title of Hydrogen-Free Process to Convert Lipid into Biojet Fuel and Green Diesel of a Nebium Phosphate Catalyst in one step. This poster consists of title, author name, affiliation and corresponding author, and also introduction, objective, methodology, result and discussion, conclusion, and lastly, acknowledgement. This slide shows the title, author's name, affiliation, and also the corresponding author of the research. Biojet fuels and green diesel are the main drop-in biofuels and the sustainable alternative to fossil fuels. These liquid hydrocarbons are derived from biomass and lack of oxygen content. It offers advantages like its hydrophobic character, higher blending rates, and compatibility for transportation and infrastructure. This study highlights Nebium phosphate catalyst catalytic efficiency in facilitating simultaneous deoxygenation, cracking, isomerization, and aromatization reaction, showcasing its potential in advancing the drop-in biofuel production for various transportation and infrastructure applications. Therefore, the objective of this study is to compare and evaluate the catalytic activity of different catalysts with Nebium phosphate, and second, to evaluate the catalytic activity of Nebium phosphate under different reaction environment.
This methodology outlines a two-step process. First, deciphering the oil composition, and second, optimizing its conversion. First, fatty acids are transformed into detectable methyl ester, separated using gas chromatography GC, and the resulting profile estimate the oil's molar weight. Next, thermogravimetric analysis TGA reveal the oil's behavior under increasing temperature. Understanding the chosen catalyst is very important. X-ray diffraction XRD unveils their crystal structure, while FTIR identifies active site for optimal cracking. With this knowledge, we move to the cracking process itself. Different catalysts as niobium phosphate, FCC, zeolites, and PDC are evaluated. Niobium phosphate is then optimized by varying reaction time, catalyst amount, and temperature under a controlled nitrogen atmosphere. Constant stirring ensure proper mixing, and centrifugation separate the post-reaction mixture. Finally, the liquid products are analyzed using GCMS to identify potential fuel fraction. FTIR confirm oxygen removal from the cracked product, a key indicator of successful conversion. This methodology paved the way for utilizing soybean oil as a sustainable fuel source. By analyzing the oil composition and optimizing the cracking process, we unlock the potential of this renewable resource.
Next, we will move on to result and discussion. Result and discussion is divided into 4 parts, which is the first one is 3.1, feedstock characterization, 3.2, characterization of catalyst, 3.3, catalyst screening, and 3.4, performance of phosphate niobium under different reaction conditions. So for the first part of the discussion, which is the feedstock characterization, the figure here shows the TG and DTG curves for soybean oil at a heating rate of 10 degrees Celsius per minute and a nitrogen flow rate at 60 ml per minute. TG is thermogravity and DTG is the derivative thermogravity. So this graph describe TG and DTG curves for soybean oil. So based on the graph, the feedstock decomposition initiated at 340 degrees Celsius and the maximum temperature of degradation occurred at 410 degrees Celsius, which is the derivative thermogravity maximum degradation temperature. So this indicated that the soybean oil contains a significant percentage of unsaturated fatty acid and making it excellent for producing biojet fuels. The second part of the discussion is the characterization of catalyst. Phosphate niobium excavated a surface area of 190 meters square per gram, pore volume around 0.3 cm cubic per gram, and show a narrow and unimodal pore size distribution centered around 4 to 6 nanometer. So the table here shows the catalyst with its specific surface area, pore size, and pore volume for the catalyst, which is we have around 5 catalysts here. The next part is catalyst screening. So niobium demonstrated superior performance in achieving high yields of liquid hydrocarbon with minimal formation of gases and coke. So niobium phosphate also considered as a good catalyst due to the high yield of linear branches alkanes, making it an excellent cold property, which is low freezing temperatures for the biojet fuels. So the table here showing the yield of liquid product from the reaction without catalyst and using different catalysts. From the original article, this is the table created in the journal, but I've recreated the data using the pie chart as we can see here, the no catalyst, niobium phosphate, FCCH, beta, ZSM5, and PDC on a pie chart. The last part of the discussion is the performance of phosphate niobium under different reaction conditions. As we can see here, we got a a figure showing a total ion chromatogram of product obtained in the nitrogen atmosphere at different reaction parameter over niobium phosphate. So starting from the bottom, we have a 0 catalyst, 7.5 of catalyst, 15% of catalyst, and 25% of catalyst. The intensity is increasing in terms of catalyst. So niobium phosphate catalyst exhibited effective deoxygenation and upgrading reaction for production of biofuels that contain a high proportion of linear and branch alkane, and also aromatic compounds. An extensive range of products can be produced or formulated with the niobium phosphate catalyst, such as biogasoline, jet fuel, and green diesel. The last part of the discussion is the performance of phosphate niobium under different reaction conditions. As we can see here, we got a figure showing a total ion chromatogram of product obtained in the
In conclusion, it was proven that niobium phosphate are the most effective due to as it efficiently removes oxygen, produce a high yield of liquid, minimize coke formation, and creates a desirable hydrocarbon profile. Achieve near complete conversion of triglyceride into a mix of biofuel in a single step without requiring hydrogen gas. This study promised a more cost-effective approach to sustainable biohydrocarbon production, presenting a promising option for sustainable fuel formulation.
Lastly, this is the acknowledgement for the study above. Therefore, this is the end of our presentation, and thank you for Dr. Rashikin and my fellow friend for staying until the end.